And once again, welcome to Bioelectromagnetics. This is actually lecture number 2, which I know many of you have already reviewed because the PDF has been uploaded, but we will actually go through the lecture today. Okay, so the question for that lecture, if you remember, and most of you had very good answers, is how does electromagnetic radiation interact with matter? And we're going to explain that during this lecture today. Okay, basic concepts in electromagnetism. We're going to talk first about Maxwell's equations at a very general level. I know we have a diverse background in this class, but we'll try to have a common understanding of Maxwell's equations or the laws of electromagnetism, which we will use to describe light, which is a general term for electromagnetic waves, quantized states of matter, light-matter interactions, how electromagnetic radiation interacts with matter, and spectroscopy, how we can detect the interactions of electromagnetic radiation with matter. And then we will specifically talk about these important terms of scattering, absorption, diffraction, transmission, reflection, and refraction. So first of all, let's talk about Maxwell's equations. There are 4 equations, and they are, the first one is basically a restatement of Gauss's law, and Gauss's law is a reformulation essentially of Coulomb's law that all of you have learned in high school, where the force, electric force due to 2 charges is proportional to the charge, or due to a charge is proportional to the charge and inversely related to the distance. It turns out that that formulation of Coulomb's law is difficult to apply in multiple charges and in electric fields. And so we have reformulated Coulomb's law as Gauss's law. And there are in the Maxwell's equations 2 formulations of this to express the twin sides of calculus: the integral equations, which present a sum of the electric field over a certain area or volume, depending on the law, and the differential equations that describe that electric field at individual points. So the integral equations describe the electric fields and magnetic fields over an area or volume, whereas the differential equations describe it at a point. But as you know from the calculus, those 2 descriptions of reality are potentially related to each other. You integrate the differential equations to get the overall form, or you differentiate the integral equations to get the point form. Now, we're not going to, this is not a course about Maxwell's equations. This is not a course about electromagnetic theory, but I just want to overview these so we have a basic understanding. Now, the implication of Gauss's law is that the electric field, let me just see here. I think we have a little bit of a problem here. Okay. Okay, can you see the screen now? This is getting a little Okay, great. Thank you for the reply. So once again, Gauss's law, the meaning of Gauss's law is that the overall flux leaving of electric field, the overall amount of electric field per volume is proportional to the charge inside, which is related to Coulomb's law. It says the electric field is related to the inner charge. The second law is Gauss's law for magnetism, which is very similar to Gauss's law for electricity. And again, there's an integral form and a differential form. And it essentially states that within a closed surface, or the divergence at a point is actually going to be zero. In other words, there are no magnetic monopoles through a closed surface. The third law is essentially a restatement of Faraday's law of induction, again, an integral and differential form. And it states that the voltage around the closed circuit is proportional to the rate of change of a magnet going through that closed circuit, or through the area enclosed by that closed circuit. So that implies that changing magnetic field through a certain region will create an electric current as driven by that voltage. So the third law of Maxwell's equations essentially connects electrical phenomena with magnetic phenomena creating electrical phenomena. And the fourth law is the opposite of that. It's more complex, as you can see. The Ampere's law states that magnetic fields can also be created by electric currents flowing. So magnetic fields can create electric circuits. That's Faraday's law of induction. And Ampere's law states that magnetic fields can be created by electric currents. So again, making that connection. So that is a brief overview of Maxwell's equations. We can also represent this pictorially. This is the charge in the center of a closed form. So the electric field is not going to be zero if we add it up around this charge, and that's Gauss's law. This is Gauss's law for magnetism, and it's indicating that around the closed area, the magnetic field going in is the same as the magnetic field going out. Faraday's law states that if we have a changing magnetic field in this area here, that will create an electric circuit going around that, or electric current going around that. And then likewise, an electric current going here through Ampere's law will create a circular magnetic field around that current. So now we go to the second part of the lecture, which talks about quantized states of matter and some basic principles in quantum physics. Many of you may already be familiar with this, some of you may not, but again, the purpose of this is to give a basic background in electromagnetism that's relevant to bioelectromagnetism. So basic concept in quantum physics, as you know, is the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle, as expressed here on the left side, tells us that it is impossible to simultaneously determine the position and velocity of a particle to infinite accuracy. In other words, the quantum world has a certain intrinsic fuzziness to this. And we can express this as a delta of a position, that's an x, and a delta of a velocity. The product of those is going to be at least some minimum number determined by Planck's constant. And that minimum number means that this product cannot be zero. In other words, the difference cannot be zero. It also implies that a bigger difference in the position implies a smaller difference or a more defined velocity. And likewise, a bigger difference in the velocity will imply a more defined position. And one way to think about this just as an idea, thought experiment, is if we want to find the position of a particle, and this is getting at the very beginning of the concept of the interaction of electromagnetism and matter, how do we know where that particle is or where that piece of matter is? Well, we need to probe it, and we probe it with some energy, and that energy will be some form of electromagnetic energy that has a certain frequency and wavelength. And as you know, the frequency and wavelength are inversely related. So if we want to have a smaller wavelength, we are going to have a greater frequency and a greater energy of the energy that goes in. So finer resolution means a smaller wavelength in order to identify it more closely, which implies a higher frequency, which implies a higher energy. And the higher energy will be more of a momentum transfer, and that will result in a greater uncertainty in the velocity. So the second part of this is on the right-hand side of this slide, quantized energy levels for electrons. So when we interact electromagnetic energy with matter, we have spectra that results. So when we are doing this interaction, we have some light that comes in, and this light has many frequencies. This is the sample. We have on the right-hand side an absorption spectrum with certain lines, and what that means is the energy is extracted from that energy coming in. So we have all these energies coming in, and on the opposite side of the sample, we have some energies taking it out. So that's why you have these lines here in an absorption spectrum. We can also have an emission spectrum. So that's going to be basically no energies except some energies that arise, and those are the three bands here. And how can we explain these fundamental spectroscopic results? How can we explain absorption? How can we explain emission? And we explain that by describing the matter as having certain energy levels. Those energy levels typically are going to involve electrons, but not exclusively so, but let's focus on electrons for now. So if we have electrons in matter, they will have some sort of position, or they will be confined in some way. The electrons are not randomly going out. They're organized as atoms, molecules, and so forth. And so that means they have some negative energy here, because if they're free to go around, then their energy is just zero here. If they're bound, they're in some stable state here. And this lowest state is going to be the ground state. And when energy is absorbed, it increases the energy of these electrons to some higher state. So in this case, very simple case, we have two energy levels here, and we have absorption. And in the case of emission, we have three, also two higher energy levels, but we have three transitions. So we have two absorption peaks and three emission peaks. So as mentioned, this describes the ground state. The ground state is the lowest energy state of these electrons. The excited state involves absorption of energy, this electromagnetic energy, and emission involves release of that electromagnetic energy, and that energy can be described by Planck's equation as Planck's constant times some frequency. So more of an energy will result in a higher frequency. So these electronic transitions, for example, in many atoms and molecules can be stimulated by ultraviolet and X-ray light. We will learn that electromagnetic energy is across a wide spectrum. So not just the ultraviolet and X-ray light, but others as well. But when it comes to electronic states in atoms and molecules, ultraviolet and X-ray light are particularly involved. Fluorescence is the process of combination of absorption, some deactivation of vibrational levels at a higher energy state, and then emission at one particular frequency or one or two frequencies. So you don't get a complex emission spectrum, you get what's called a fluorescence spectrum. So a very important distinction in electromagnetic radiation is the distinction between ionization and non-ionization. So some electromagnetic radiation, if it is of sufficient energy, will actually ionize atoms and molecules. And a certain amount of energy is required for that ionization. And we call this ionizing radiation. And typically it's in the ultraviolet X-ray region. And then there's non-ionizing radiation, which does not have enough energy in a quantum level to eject electrons from the atoms or molecules. And this non-ionizing radiation is typically in the radio frequencies, the infrared and the visible lights. And we're going to talk a lot about the difference between ionizing and non-ionizing radiation. So as mentioned, ionization is the energy required to remove an electron. And we have some ionization energy that takes some element, a molecule or an atom or an element, and then you ionize that, the electron is ejected, and you end up with a positively charged atom or molecule remaining. And that ionization energy, again, is the energy required to go from some ground state, but instead of some intermediate higher energy state, it is the energy to go essentially to a free electron, which is a zero energy state. In the periodic table, you have relationships of ionization energy. So some things are more easily ionized. Some elements are more easily ionized. Some elements are more difficult to ionize. And that's related to the size of the element. So for example, you go down in a column or group, I should say, in the periodic table, the ionization energy will decrease because the atoms are bigger and it's easier to pull away the electrons. As you go horizontally along a row of the periodic table in the elements and the atoms, the ionization energy will actually increase because the atoms get tighter and tighter, get a smaller diameter. So there's different types of radiation will ionize, higher energy radiation, and also the ability of a certain matter to actually ionize will also depend on its atomic and electronic properties. Now we talked about Maxwell's equations. The four equations are Gauss's law, the law of magnetism, Faraday's law of induction, which says that a changing magnetic field will influence and create an electric field, and Ampere's law, which says that a current will also create a flowing charge, will also create a magnetic field. So this will lead, as we'll see shortly, to the concept of electromagnetic waves. But before we talk specifically about electromagnetic waves, let's talk for a few moments about waves more generally. So what are waves? Waves are a disturbance in some medium, mechanical waves, such that each particle in the medium vibrates around an equilibrium point. This is the fundamental concept of a wave, which will then apply to electromagnetic waves, but these are mechanical waves. So you imagine a object in water, for example. This is a ball sitting in the water. If you press it down, then there will be a force, a buoyancy force pushing it up. And then as it goes up, there will be a gravitational force pulling it down. And that represents an oscillation around an equilibrium. So that oscillation around that equilibrium will then propagate similar forces next to that point, which will again cause that point to go up and down and be influenced by the same forces as we described. And therefore, you can imagine that a perturbation or this disturbance in one point if it's connected to other points, will create a wave. These waves can be transverse waves, where the motion is perpendicular to the direction of the wave. They can also be longitudinal waves in which the motion is in the same direction as the wave. And longitudinal waves are seen in sound waves or other forms of mechanical waves through mechanical media. We will focus on transverse waves because those are the type of waves that are described or occur with electromagnetic waves. So when we go now into transverse waves, we have, as I implied earlier, certain properties. And there are three basic properties of waves. One is the amplitude, or how big the wave is. And that's described in this graph here. You can see here the amplitude going from the 0 point to the peak. And of course, on the opposite direction to the negative peak, because a wave represents an oscillation around some 0 point or equilibrium. The second is the frequency, which represents the number of times or cycles that this wave progresses in a certain unit of time, typically seconds, and then a phase shift relative to some arbitrary starting point. So those are the three basic properties of transverse waves, and by extension, electromagnetic waves. A very important property of these general property of waves is that their frequency, or how fast that they oscillate in a certain period of time, is inversely related to the wavelength. So in other words, a very high frequency, such as X-rays, will result in a very small wavelength. So when we talk about interactions with matter, as I mentioned, if we want to get smaller and smaller dimensions relative to that matter, we have to use smaller and smaller wavelength, and thus higher and higher energies. So it's no accident that we use X-rays, for example, to probe the structure of atoms, of molecules. Whereas we cannot use light waves, which have a much longer wavelength, to actually look at molecules and their structure. We can look at much bigger structures. So we describe these transverse waves by trigonometric equations because they actually map out very precisely the form of a transverse wave. And again, a trigonometric equation will have the mathematical equivalent of what I just mentioned: an amplitude, a frequency, and a phase shift. And then the specific relationship between the frequency of the wavelength is given by this equation, which says that the frequency is equal to the speed of propagation. And in the case of electromagnetic waves, this will be the speed of light divided by the wavelength. So you can see this inverse relationship here. Now, multiple waves, for simple approximation for the time being, we can say linearly superimpose, or superposition. So different waves will basically add up with their amplitudes to give a net wave. And these are two examples where the phase shift is, the waves have the same amplitude, they have the same frequency, but a different phase shift. So when they are in the same phase, the phase difference is 0. Then the waves will simply add up to form constructive interference. And if the waves are entirely phase shifted by 180 degrees, or a half of a cycle, they will be opposite each other and they will undergo complete destructive interference. And this is just a linear sum of their amplitudes. Obviously, when the waves have different frequencies, it will be more complex, but it will be a linear sum. We have nonlinear wave phenomena, which we'll talk about in a later lecture. So now let's put those two concepts together. We talked about electromagnetism, starting out with Maxwell's equations and talking a little bit about quantum mechanics. We talked about the very basics of waves and some of the mathematics, transverse waves, and so forth. Now we will put that together and we'll talk about electromagnetic waves. So as I mentioned, a wave is a perturbation of that then propagates outward. A mechanical wave will be a perturbation of, for example, a ball standing in the water, or it will be air molecules relative to sound. And electromagnetic waves are not mechanical waves, but the same concept of a perturbation influencing the nearby environment and then spreading out applies to electromagnetic waves. So if you recall Maxwell's equations, where we had the last two Maxwell's equations, Faraday's law and Ampere's law, they showed a connection between a changing magnetic field and electrical phenomena, and changing electrical phenomena and magnetic phenomena. So you can imagine that if you have some charge that's accelerating, that accelerating charge by Faraday's law will create a changing magnetic field. That's indicated here. And then by, Ampere's law will create a changing magnetic field. And then that changing magnetic field by Ampere's law will create a changing electric field. And then the changing electric field will influence a changing magnetic field, and so on and so forth. So we have a perturbation that will then expand out in space. And that generates, as shown here, a wave. So this depiction here is meant to encapsulate those two the third and fourth laws, the second half of Maxwell's equations, Ampere's law and Faraday's law. It's meant to encapsulate that interaction between magnetic fields and electric fields in order to create a self-propagating wave. And just like the general waves that we talked about before, they can be described by an amplitude, by a wavelength and a frequency, and in this case, the speed of that will be the speed of light, and an inverse relationship between the wavelength and the frequency. So here we have the electromagnetic spectrum. This is one of the essential concepts that we have to understand. This electromagnetic spectrum states that this phenomena of accelerating charges and perturbation is going to be the same fundamental phenomena whether we are talking about radio waves or gamma rays. And this mutually interacting magnetic and electric fields creating a wave will be the same phenomena for any of these energies. But of course, we all know that gamma rays, very high energy, have a very different behavior than visible light, which is the light around us, of course. And of course, they are very different than radio waves. In particular, as we know, gamma rays, X-rays, and most ultraviolet light is ionizing. And the visible, infrared, microwaves, and radio waves are non-ionizing. So on a very basic level, these are almost like different phenomena. But even though they're very different phenomena, X-rays are not the same as visible light, fundamentally they are the same. And they differ entirely or only in their frequency. And because there's a relationship of frequency, they differ in their wavelength. So this is a very interesting phenomenon. Why should something that's essentially the same, but only differing by frequency, have so much varying behavior? Why are X-rays so dangerous? Why are X-rays used in X-rays, like a CT scan? Why is visible light used to create beautiful colors and paintings? Why is infrared light used in the airport to test for fever, to screen for COVID-19 patients or people or infected or other diseases? Why are microwaves used to heat your chicken in the microwave oven? Why are radio waves used to communicate by radios or smartphones and so forth? So why all this different behavior? And the fundamental answer is that the light, or I should say the electromagnetic radiation, will interact in many different ways with matter. And that relates to the ground state we talked about, relates to the excited state we talked about in a very basic way. But I wanted to give that background because if we want to understand how this radiation can be so different and have different personalities, if you will, it is because it interacts with matter in different ways. And we will explore all these different ways that it interacts with matter to help give a framework to understand that. And of course, the most important matter that we are interested in this course, bioelectromagnetics, is how all those different waves interact with biological matter. So in a later lecture, we're going to talk about biology, cells and molecules and so forth, so we can really understand and have a good vocabulary and the basic framework for understanding biology. So then when we talk about X-rays, or we talk about ultraviolet, or we talk about visible light, or infrared, or microwave, we'll start to have a feeling for how that radiation interacts with that matter in a different way. So to summarize, the gamma rays have a high frequency, a short wavelength, and a high energy. The energy is proportional to the frequency. On the very opposite end of the scale are radio waves, which have a very low frequency, a very long wavelength, and a low energy. Gamma rays in general will interact with the nuclei of atoms, and they can cause ionization and atomic changes, nuclear changes, so they can be quite dangerous. And in medical terms, they can cause cancer, and we'll talk about that in a later lecture. X-rays do not interact with the nucleus of atoms, but they interact with the inner, tightly held electrons. Remember, the ionization energy is related to how close those electrons are to the nucleus. So X-rays interact with these inner electrons. And we'll talk about why that is dangerous, why it can also be useful for X-rays and so forth. And then ultraviolet light interacts with outer electrons, as well as electrons in some molecules. Visible light will interact with electrons in certain types of molecules that look colorful, as well as in transition metals. Infrared will be related to molecular vibrations, so it's not electrons per se, but groups of electrons moving. And microwaves will relate to molecular rotations in general, and radio waves will relate to electronic transitions of very low energy electrons that are typically in conductors. So let's talk about the relationship, a little bit more detail of these electromagnetic waves and Maxwell's equations. These are the Heaviside form of Maxwell's equations. They are differential forms. So this is Gauss's law. This is the Ampere's law. This is the magnetic law, and this is Faraday's law of induction, and this is Ampere's law. So this is, we're not going to talk about this in detail, but these are various vector quantities that can describe this in a differential way. So again, the Maxwell's equations, the second, the half, the third and fourth ones in particular, are going to describe this interaction between magnetic and electromagnetic fields. So now let's focus a little bit on visible light. Visible light is a component of the electromagnetic spectrum, varying between the violet, which is the highest frequency, highest energy, shortest wavelength, all the way to the red region, which is the lowest frequency, longest wavelength. And in between that, we have different colors here. As I mentioned, the wavelength is inverse to the frequency. So the visible spectrum is flanked by the infrared region on the lower frequency side, and the ultraviolet region on the higher frequency side. So let's give some examples of the interaction of radiation that we use in biology and medicine. One example is use of non-ionizing radiation and transcutaneous electrical nerve stimulation, essentially a form of radio waves, a low frequency electrical current that actually stimulates peripheral nerves on the skin using various electrodes. And it's a non-invasive way of doing pain management. So you might ask, how does this manage pain? And we will talk about it in more detail in a later lecture. This is more just for overview. But these low frequency radio waves will interact with certain nerves that will send signals to the brain of some input. Those nerves are not the same as the pain receptors, and the pain receptors will be sending their own signals. But the theory is, it's called the gate theory of pain, is that stimulating some nerves will distract the brain, if you will, distract the nervous system from feeling the pain signals. It's the same thing if you have a baby or a small child who fell down and they're crying and they're in pain, but then you say hello to them and you make a smiley face and you play with them, they get distracted and they stop feeling the pain. Not exactly the same concept, but it's an analogy where this transcutaneous electrical nerve stimulation will create a kind of confusion or distraction for the nervous system, and that will decrease the pain that's being experienced. So the current TENS therapy has several specifications to that electrical current. The waveform, not always a sinusoidal frequency. Of course, the frequency of that radiation, how wide the pulse is, and also the amplitude or intensity. And again, this is building on what we talked about with electromagnetic waves. Frequency and amplitude are important principles. So here's another example. It's called radiofrequency ablation. This is some sort of cancer or tumor under the skin. This is the epidermis. This is the subcutaneous fat. This might be some tumor underneath. You have a radiofrequency ablation probe. Ablation refers to destruction, and radiofrequency, obviously, there's a radio frequency in the radio wave region. So as you know, radio waves are not necessarily dangerous. We have radio waves all around us. Smartphones create radio waves and so forth. But these are very low intensity radio waves. The radio frequency ablation has a very high intensity radio wave. And that high intensity radio wave will create be ultimately converted into heat energy, and that heat energy will kill that target tissue or the cancer. So in order to understand this process, we have to know about absorption, we have to know about scattering, we have to know about energy transitions, because obviously radio frequency is different than heat energy. Heat is at a higher energy, so how does this radio waves ultimately get converted to heat? We see a similar application in, this is a liver cancer, so the probe will go a little bit deeper, and again, it inserts into a tumor. There might be ultrasound, which is not electromagnetic waves, but the sound waves, and that ultrasound is locating the tumor, so the radio frequency probe is inserted there, and again, a high intensity radio wave is created or generated, and then that ultimately is converted into heat energy that destroys that target tissue. So we talk about X-rays. We talked about radio waves, radio frequency ablation. X-rays, as you recall, are high energy waves produced by transitions from inner electron shells. So as we had that slide about ionization energy, if we want to pull an electron away from an atom or a molecule, if that electron is closer to the nucleus, where there's a positive charge, it will be much harder to pull away. So X-rays are relatively high energy electromagnetic waves, so they interact with these inner electron shells. There are other ways of generating X-rays from the deceleration of rapidly moving electrons, but for the purposes of bioelectromagnetics, this first point is the most crucial. And again, high frequency, short wavelength, high energy. Now, why are X-rays so useful? So X-rays are used for imaging. This is Röntgen's original X-ray in 1895. This is his hand. This is the ring. We can use X-rays for imaging in industry as well. As I mentioned, the wavelengths are very short, so we can use it for atomic and molecular structure, determining where are atoms. We can also use it for electronic structure and bonding, so where are the electrons? And we can even use it for determining magnetic structure and properties. But this first one is most critical for bioelectromagnetics, using for imaging. So this is interesting. If you have an X-ray, you can see the bones, as you can observe in this slide here. You can see blood. Bone and blood are the two major tissues that are observed by X-rays. You don't see everything, of course. You see bone and blood. Why is that? Well, as I mentioned, X-rays interact with inner electrons. And most of biological molecules, as we'll see in a later lecture, are composed of carbon, oxygen, nitrogen, and hydrogen. These second row periodic table elements do not have a lot of inner electrons. So X-rays actually goes very transmitted through the body quite easily, and they are not absorbed by these second row elements, carbon, nitrogen, oxygen, and hydrogen. But the body has some heavier atoms that do have significant numbers of inner electrons. And those in particular are calcium, which is found in bone, and iron, which is found in blood. So the reason you start to see some absorption of X-rays in biological tissues is largely because of the presence of calcium and iron. In other words, heavy atoms with lots of inner electrons in certain parts of the body. Of course, there is some amount of X-rays absorbed by second row elements, carbon, nitrogen, oxygen, hydrogen. But in general, there's not a lot of absorption. It is more with this carbon and iron. So as I mentioned, X-rays are very important in electromagnetic-based diagnosis. X-rays were first discovered in 1895. We also did cardiac catheterization, which is able to look at the heart with X-rays, with a coronary angiogram. CT was invented in 1972, and multi-slice CTs. We'll have a later lecture that will explore X-rays and X-ray imaging and CT scans in more detail. So we went from radio waves to X-rays, and now let's talk about radiosurgery. As I mentioned, gamma rays are very high energy, and they can damage biological tissues, and we will talk about how they damage biological tissues later, but primarily, of course, through this ionization. And we can use that damaging property to kill cancer cells. But of course, this is a physical interaction, so if you kill cancer cells, you can also kill normal cells. So that raises a challenge. How can we get the gamma rays to kill cancer cells and not kill normal cells. As we'll talk about in later parts of the course, there's a relationship between the dose of radiation and the response. We call that dose-response ratios. So there's radiation always around us, but we don't get adverse effects because the dose is very low. But as the dose gets higher, such as in a nuclear accident or a nuclear bomb, or with therapeutic X-rays, if the dose is high enough, we will get damage. So radiosurgery is the process of creating multiple beams of gamma rays that, through their geometry, converge and concentrate on a target, which may be a brain tumor in this case, so that the normal tissue that it's traveling through, as you can see here, the normal tissue is not affected by this gamma rays, but the concentrated effect is at the tumor target. So these are the radioactive cobalt sources, converging gamma rays, and you have a target here. So let's talk about some general principles of interaction of radiation with matter. This is a summary, and we'll go through these very quickly over the next 10 minutes, and then we will finish for the next lecture. So transmission is the process by which the electromagnetic energy goes through an object. Reflection is the process by which the electromagnetic wave is reflected from the object, as you can see here. Refraction is the process by which the direction of the electromagnetic radiation is altered when going through the object. Diffraction is the process by which that electromagnetic energies are spread out when they go through the object. Absorption is the process by which that, adsorption, excuse me, is the process by which that electromagnetic energy is absorbed and then released in a different form. And scattering is when that electromagnetic energy is scattered all in many different directions. So the principle of all of this is based on the interaction of photons with electrons. And we have two types of electrons. We have core electrons, the inner electrons, as we mentioned. Those are mostly interacting with X-rays. And then we have the outer electrons, or valence electrons, which are mostly interacting with ultraviolet and visible light. So when a photon, here you can see, is absorbed, or when a photon interacts with matter, it can be absorbed, it can be scattered elastically or inelastically. Elastic scatter is at the same frequency. Inelastic scatter is at a different frequency. We can also have the electron being emitted, or ionization. We can have the electron excited, or we can also have the electron de-excited. So these are all possibilities that occur when an electromagnetic radiation interacts with these electrons in the target matter. So here's some energy diagrams related to how photons interact with the matter. We have, this is an energy diagram in a little more detail. We talked about this in simple terms earlier. Absorption is the process by which you go from a low energy state to a higher energy state. Multi-photon absorption is multiple stages. Fluorescence, as I mentioned, is excitation from the absorption, vibrational relaxation, and then fluorescence down to a ground state or lower levels. Elastic scattering is the radiation is absorbed but quickly emitted at the same frequency. Stokes scattering is when the radiation is absorbed and then emitted at a lower frequency. So in other words, some energy is absorbed by the matter. That would be this difference here. And anti-Stokes scattering is when the photon is absorbed but actually emitted with a greater energy. So these are some energy diagrams related to that. So absorption is basically the process by which the energy is absorbed by the matter, will be then either turned into another form of radiation, another energy of radiation, and that's to be distinguished from reflection and transmission. So that's absorption. This is an absorption curve of terahertz radiation. Terahertz is between the microwave and the infrared. We will talk about that more in a later lecture. And you can see there's more absorption, the absorption coefficient in inverse centimeters at higher terahertz radiation, and there's less absorption at lower radiation. The dotted line is the reflective index, so you see more reflection at lower terahertz, and you see less reflection, more absorption at higher terahertz. So there's a roughly inverse relationship between absorption and reflection. So another example of biophotonics in this absorption is photodynamic therapy for acne. This is acne on the skin, and you can see it's cleared up with photodynamic therapy. You have a light source, and you have bacteria and a drug called ALA, and the light source will activate the drug to kill this bacteria. And we will talk about photodynamic therapy in more detail later. So that's an example of absorption by those molecules to activate them. So what is scattering? There are different forms of scattering, but basically it is radiation coming in and the light being emitted in all directions as opposed to just purely transmitted or reflected. So we have actually different ways that the light can be emitted from this matter. You have the incident light, you have reflection, you have transmission, and you can also have scattering. That scattering is going to have a certain frequency. You can have Stokes scattering, which has a lower frequency or higher wavelength, or you can have anti-Stokes scattering, which has a shorter wavelength or a higher energy. Reflection, as I mentioned, is you have light basically bouncing off at the equivalent angle of incidence to the angle of reflection. That results in different mirror properties. We don't need to talk about this in detail. And diffraction occurs because you have mutual interference of waves emerging from a single point. And so a single slit diffraction will result in a pattern, as you can see here. A double slit diffraction experiment will result in successive intervals of constructive and destructive interference, as you see in the lower right-hand side. Dispersion is the variation of the velocity of light as it goes through a medium, and that dispersion will be related to the frequency of the light and also related to the material, and that dispersion will result in refraction. And that refraction means that the angle of incidence will be different than the angle of refraction. If you're going through a more dense material and the velocity will decrease, the speed of the electromagnetic wave will decrease, you will see a movement towards the normal or a decreased angle of refraction. If you're going into a less dense medium, then the velocity will increase and you'll see an increased angle of refraction. So some examples, basic principles of spectroscopy. We talked about this earlier, but I want to emphasize very simply, we have a sample and an incident white light with many frequencies. We get an absorption spectrum or an emission spectrum. That's the fundamental spectroscopic experiment. And as I mentioned, we can have different forms of spectroscopy: elastic scattering, inelastic scattering, electron emission, or the photon being absorbed. I wanted to mention one thing with COVID-19. I'll talk about this later, but you know the virus obviously can be on surfaces, it can be in the air, etc. If we were to do some form of spectroscopic experiment where we could have a certain type of electromagnetic radiation that would detect certain types of molecules related to that virus, we could have a method to detect the virus on the surfaces or on people and so forth. We don't have those type of tests. We have physical matter-based tests. The PCR test that Korea uses is based on a genetic test, and there are also antibody tests, but there are no spectroscopic tests for the virus. And that would be a very important advance, obviously. If we had a spectroscopic test for the virus, many things would be very different. So one way we might have a spectroscopic test is based on the principle of protein electrodynamics. Proteins are vibrating. They are the machinery of life. They are around these viruses, for example. Proteins are charged. We also know Maxwell's equations, which we talked about in the beginning. That means that proteins will be emitting radiation. Proteins will be absorbing radiation. And we call this protein electrodynamics. So if there was a way to specifically detect the vibrating protein specific to this virus, the COVID-19 virus, SARS coronavirus 2, then we could have a spectroscopic method, for example, reflection spectroscopy or transmission spectroscopy of detecting the virus. So I want to end with a closing thought. Richard Feynman is a famous physicist, and he wrote that everything that living things do can be understood in terms of the jigglings and wigglings of atoms. So these atoms and molecules are vibrating, but as I mentioned, vibrating charges, by virtue of the Maxwell's laws that we started with, will create electromagnetic radiation. And we also know that that electromagnetic radiation can interact with those charges through absorption, emission, Stokes emission, anti-Stokes emission, all those principles we talked about. So bioelectromagnetism would be a very powerful way, is a powerful way, but even more powerful way of understanding the basic functioning of life. So next time we are going to focus on more concepts in electromagnetism, time domain electromagnetic fields, frequency domain electromagnetic fields, conduction, polarization, magnetization, energy absorption, and various computational methods. So, and as I mentioned, the question for next week, which most of you already answered, describe the difference between time domain and frequency domain electromagnetic fields. We will discuss that. So the question for today is, how does light interact with matter? I hope we covered some of that today. It's not so simple, but we've learned some basic principles of how light, photons, is a wave. It interacts with electrons. It can be absorbed. It can be emitted in different frequencies. It can be scattered. It can be refracted and reflected, and so forth. So thank you very much. Let's keep this window open, and we will start again at 3:10, and we'll finish with lecture number 3. Everyone okay? We will start again at 3:10, and we will do lecture number 3. That will be a shorter lecture. We will end before 4.